Greetings, my name is Faiz and we will present our work titled Learning-Based Optimization of Atomic Arbitrage in Decentralized Financial System. This work is done with Dr. Huned Materwala and Professor Davor Svetinovic at Khalifa University. We first discuss our research problem, which involves DeFi, MEV, and arbitrage, and why MEV arbitrage matters in DeFi. DeFi, or Decentralized Finance, is a financial service that runs inside blockchain smart contracts. In this DeFi environment, MEV, or maximal extractable value, refers to additional profit that can be extracted from a transaction. One major MEV strategy is arbitrage, which involves buying and selling asset or token across different pools or exchanges to exploit price differences and to make profit. Here we discuss the specific arbitrage pattern that we studied in this work, atomic triangular arbitrage, which means we execute the tree swap in the form of a loop cycle as one transaction. We start with the token A, swap to the token B, then to token C, and finally return to the token A. The loop must be profitable only if the final amount of token A is worth more than the starting amount after deducting the fees and transaction costs. If the swap is not profitable, the whole transaction is skipped. In the period of November up to December 2025, arbitrage reached more than 3 billion in trading volume and 21 million in profit. So this market significance motivates us to study arbitrage. Existing works rely on simplifying assumptions that may lead to overly optimistic profit estimation when deployed in real-world DeFi environment. To bridge this gap, we propose an atomic triangular arbitrage optimization problem formulation that explicitly incorporates realistic DeFi constraints. C1 requires positive profit, C2 limits swap by the available wallet balance, C3 limits swap based on the available amount in the pool reserve, C4 and C5 enforce the correct triangular flow, meaning each swap uses the previous output and the final output returns the starting token. C6 limits the timing to the blockchain 12-second execution window. During the arbitrage, we must choose triangular paths to maximize profit as much as possible, but we must follow the rule CPMM or constant product market marker formula, a smart contract mechanism that defines the price of each swap based on the existing token supply and demand, from which our gain may become lower than we expected, and at the same time we must pay high costs. Hence, this made the problem challenging. The diagram shows the sandbox environment, which represents the dataset sources, wallet balance, token price, pool reserves, gas price, and our proposed mathematical formulation constraints. In this work, we use a specific DRL algorithm, PPO, or Proximal Policy Optimization, which learns a policy or decision rule to select a path and a trade amount without evaluating all possible combinations during the deployment. Our sandbox environment uses Uniswap v2 and v3, token price from CoinGecko, gas model data from Zero MEV and Etherscan, and we set the swap fee as 0.3%. In the experiment, we compare PPO against 4 search-based baselines. Grid search is exhaustive. Greedy selects the local best options. Beam search retains only the best partial path as it builds the triangle loops. The heuristic method ranks candidates first and validates the top options, and the same main metrics are reported: profit, ROI, share ratio, and the inference time. We developed the whole experiment using Gymnasium and Stable Baselines library. From our experiment, the mean profit increases with the wallet balance for all methods. Grid search achieves the highest profit of $13,000, while PPO achieves $4,000, outperforming the greedy, heuristic, and beam, indicating that the grid search is the offline upper bound and that PPO captures the strongest practical profit among the baseline. Similarly, in ROI, grid search maintains the highest ROI with PPO at a medium level, while greedy, heuristic, and beam stabilize at the lowest level. This indicates that the CPMM rule limits the percentage returns for all methods, but again the PPO survived the impact. In the share ratio, all baseline achieve high values, indicating over-optimism under real on-chain conditions. In inference time, grid search has the highest inference time with 200 seconds due to the exhaustive search for arbitrage opportunities. In contrast, PPO other baseline complete inference under 100 milliseconds. Therefore, while grid search represents the upper bound on achievable profit, the PPO gives the consistent profit with millisecond level decision time, making it the most effective practical approach. The conclusion is that the exhaustive search can find higher theoretical profit, but it is too slow for on-chain execution. Meanwhile, PPO gives consistent positive profit with millisecond-level decision time. Blockchain condition can change within a second, and inference speed is critical for on-chain arbitrage. Therefore, despite lower profits than grid search, PPO offers more practical balance between profitability and execution speed. Thank you for listening.